So welcome. Yeah, we started off a little bit last time and we talked about basically this idea about light being energy. The energy depends upon the frequency, and the frequency is basically the color. And we talked about how people pretty early on figured out a decent value for the speed of light. Romer had an astronomical method, and then Fizeau was the person who did the tooth and gap spinning wheel method, and got pretty decent values in both cases. Looking back, we'll see that good old Newton had a go at a fair amount of work in optics. And the thing I find astounding is that you look at a lot of what he wrote, and we're using the same information given in the same way, even down to this day. It breaks down into two things: reflection and refraction. So we have the law of reflection. The angle of incidence equals the angle of reflection, and the incident ray, the surface normal, and the reflected ray are all in the same plane. So they're all on like a piece of paper. And then when you get transparent materials, the light can go through the transparent material. It does not change color unless the transparent material has a tinge to it, but it doesn't change color. So blue light goes through, transparent material, comes out as blue light, etc. But it does slow down, and so if you get a change in speed and you're not changing your frequency of walking, then you must be taking different size steps. And in terms of that analogy, it's the wavelength that's changing. So I can characterize the transparency of a material by how much it slows down the speed of light, and I come out with a number called the refractive index. And the refractive index is a number which has no dimensions. It's basically speed over speed, if you like, and it's got a number that's greater than 1. Or I can characterize the same numerical value, the figure of merit, in terms of the wavelength, how the wavelength changes, how the speed changes is the same as how the wavelength changes because the frequency stays the same. I can see that when I get a ray of light approaching a transparent material at an angle. So this is a little bit different. I'm looking for my pen here. It comes in at an angle. What I can see is that I get some kind of bending effect. And we didn't talk about it. I didn't explain that at the time. So let me actually just, in a hand-waving way, explain a way of visualizing what's going on. So we'll do that, and we'll go there. We'll do that, and we'll do that. So here we go, and cancel. Oh no, yeah, okay. And then I'm going to do this. So, yeah, okay, that one. So I'm going to go here, and there's my interface, and then let's get our light coming through, and let's have light coming down as a beam of light. And I know that I am in air, which is just like vacuum, really, as far as light's concerned. And so I have a very high speed. And so imagine a whole row of soldiers marching. And these are the steps that they're making. Very nice. Nice in line. What you see is that this soldier at what is, to me, is the left-hand side, basically reaches the interface first. And to make the analogy, let's say that this is like asphalt. Well, concrete. I can spell concrete. And then this is sand. Okay? You can't walk as quickly across sand as you can across asphalt. So what happens is this soldier starts stepping into sand. And what happens is that they go slower. Now, because the soldiers are lined up, let's imagine that they're arm in arm. I have no idea why they should be arm in arm, but they're arm in arm. So what happens is this guy goes slower and he drags the others back. But these guys are not affected yet. And then this guy can't step as far because it's on sand. And so, whoa, and it goes like that. And then this guy can't step as far, and it goes like that. And then you start going like that. So that's one way of visualizing. That's the way that I was taught. Very militaristic way. There's another way, which is you have a pair of wheels connected by an axle, and they're just traveling in that direction. What happens is, as this wheel hits the thing, I think intuitively you know that this thing goes that way. Now, that is going from concrete, which is fast, to sand, which is slow. But it gives you this idea that when you go from air, say, to water, the refracted ray bends towards the surface normal. If I went from, say, water to air, it's hard to imagine, the bottom of a bubble, then what would happen is my ray would bend away from the surface normal. It's always awkward about which way around do you get it. And you could figure it out from doing this kind of thing, but, you know, hey, we want to go a bit faster than that. And so what I always suggest is that you remember one version of it really well, get comfortable with that, and then do the changes if I ask you something different. Yeah. So if I asked you, say, oil and diamond, you'd go, well, am I going to a bigger refractive index or a small refractive index? Oh, I'm going to a bigger refractive index. Oh, it's just like air and water then. The numerical value might change, but the tendency is the same. Yeah. So this kind of like wave way, it's a wave way of looking at things. This is where you don't think of the beam of light as being a series of particles of light. You think of it as a continuous flowing wave. It's something that there's been a big debate over the years about. Newton was a particulate person, corpuscular theory, and Huygens was a wave theory person, and they argued backwards and forwards. So we didn't talk about that, but that's kind of where that kind of thing comes from and how you can kind of like get comfortable with it. And the rest is kind of like just detail, isn't it? We can talk about the fact that the refractive index is not precisely the same for a transparent material with different coloured lights. There's slight differences, and that leads to the rainbow effect we get with a prism. And we call that dispersion, and we can talk about how a prism is a really clever piece of glass because it has two interfaces where we get refraction, so it kind of like doubles the effect. It doesn't literally double the effect, but we get two bites of the cherry, and so we see the effect even more, which is why we see the dispersion effects very clearly, whereas with other systems we would not so much. So it's really kind of great. It's a great system to have. And then we did a bit of math on that. Well, it's just throwing math at you. And then we talked about how this is actually technologically incredibly important because although we don't use the prism anymore, we use a thing called the diffraction grating, that being able to split light up into different colors is amazing because when we have in atoms, when we have the electrons moving from different energy levels, they often give off light in terms of photons of color. Some which we can see, some which we can't see. And so we can do analysis. It's almost like a fingerprint for each different species. So it's an amazing system. And we just talked about the traditional student spectrometer. You know, most students of my generation spent a fair amount of time staring into these things. And this is the modern day equivalent where it's done basically electronically, and you get a graph out rather than just looking down and seeing a bright light or a darkness. So it enables you to do some tremendous analysis. There's other things where you get these weird effects. So if you're actually, for instance, in a swimming pool and you look at a big glass window, then you will see a hole in the glass where you'll see reflected fishes all around you. But there's this one region where you're looking straight ahead and you'll see everything in that room kind of through a fisheye lens because you can see that the light, I'm doing the light going away from you, but you can imagine it just as well coming towards you. And you see that the things at the side will appear here, the thing on the side will appear there, then So everything's crunched up in the middle, which is a classic fisheye lens. And so we can talk about the critical angle, which is the angle of incidence, which gives you a 90-degree angle of refraction. So again, it's Snell's law. We've been there. And then we can talk about total internal reflection. It turns out that once you go beyond the critical angle, no light is refracted. If you think about it, what can you get that's more than 90 degrees? It's kind of like you're not, that system is turned off, and so all you get is reflection. All the light must be reflected. And that is better than a mirror. And so when you want to make a viewing instrument that has kind of large light gathering objective lenses and eyepiece lenses that are the width of somebody's head, you've got an alignment problem. And there's a few other things going on as well, but this is one thing. And so you could use a mirror here and a mirror there and have the light come in and bounce off and go like that, and the light come in and bounce off and go like that. You could do all that with mirrors, and that would be the cheap way to go and the light way to go. But if you want to get really good optics, what you'll do is you'll use two prisms. And the light will come in and it will reflect off the back surface because you're beyond the critical angle, and it'll reflect off the back surface and so on. And that's why binoculars have the shape they have. And that's why they have the weight they have to some extent. There's a fair amount of glass just in that reflection. A periscope. Periscope, rather than using mirrors, rather than using mirrors, you just use two prisms and you can get it. Very nice. So let's now talk, this is new, so let's talk about rainbows. So they're a bit more complicated than we might think. The light comes in and it's refracted at the front surface as it comes in. It is reflected at the back surface because you're beyond the critical angle, and it's refracted at the front surface on the way out. So there's two refractions and reflection taking place in the light. And light being what it is, we can very carefully analyze and see what the angles are between the incoming ray and the reflected ray. And it's like 40 degrees and 42 degrees. So there's a 2-degree difference between the violet and the red light. Notice the sunlight comes in and the rainbow is reflected back. So you'll always see rainbows when you look away from the sun. You won't see them looking into the sun. That's, so you tend to see them in a place like Tampa. You'll tend to see them in an afternoon when the rain is to your east and the sun is setting to the west. So you'll see them over Brandon as opposed to over the bay in an afternoon. In the morning, we often get rainbows in the morning. Sometimes we do, but you'll see them going the other way. If you're on a plane, when you're flying through the water vapor, through the clouds, through the water droplets, basically, you'll way through the water vapor, you will sometimes see the full rainbow. It's the same principle. It's just you're looking at light that's been reflected out of water droplets. So if you look at this, well, this implies, if you're not careful, you might think that the violet is going to be on top and the red is going to be on the bottom, but rainbows always have red on top. If you like, you do the Richard of York going downwards, so you can read it nicely. That's the way it looks. And why is that? Well, it's because you see this from a whole bunch of droplets, not one droplet. And so you'll see the red coming out of the droplets near the top because they go at a more downwards angle. And you'll see the violet coming out of the droplets at the bottom because they're coming out at a shallow angle. So that gets people confused sometimes. Okay. Technologically, this is really useful for things like fiber optics. I actually found some fiber optics in my garden when they were. So from what I gather, if you go backwards and forwards between the different digital companies, there's sometimes sort of playful rivalry takes place, or not playful rivalry. One time when I first got my house, the person came to set up the cable, and they said that the competition had cut all the wires, so that for their system, so they did damage to each other. It's like, back in the Wild West of, cattle rustlers and So I don't know what your yard's like, but my yard is like, it's like a graveyard for cables. They're all over the place, and half of them don't work and all that. And so I was digging in the garden. When you see a cable, I've learned not to pull on the cable too much because you might be pulling out your internet, But there was this fiber optics cable. And I remember the guy told me he'd buried it quite deeply, so I took the risk and yanked on it. And so I got some fiber optic cable, which I'll bring in if I remember. Tiny little cable, big wire, because it's kind of like you don't want it to get damaged. So we did a couple of examples which we did, and then let's do this last little bit, which is ray approximation to geometrical optics. There are times when we really want to look at the wave nature of light, and there are times when we really want to look at the particle nature of light, and it's no big deal. And so here we're looking at the particle. We're looking at the wave nature of light. So rather than imagine this as a series of photons, we imagine this beam of light as just a continuous parallel stream of parallel, like wavefronts, like Huygens would have thought of them. So imagine you're at the beach and you're looking down from an aeroplane. There's all these wave crests coming steadily towards some kind of barrier. In a lot of optics, you want to define the edges of your beam well. If we look back here, what makes this particularly relevant is that we have a series of lines. And we have the series of lines because of that slit. If you imagine, what we're doing is we're imaging that slit. And behind it, there's a light source, and the light source is going to be kind of diffuse. Most light sources are somewhat diffuse. And so we aperture, we collimate that light source using opaque baffles, basically. We do that very often. We just put a piece of metal on one side, piece of metal on the other with a narrow hole. Because otherwise what we do is we'd get that would spread out, and that would spread out, and that would spread out, and that would spread out. And they would overlap each other. And so there's this game you play, and the same comes actually with mass spectroscopy. The same game comes with mass spectroscopy. Although that's a mass to charge a flight path through a magnetic sector or whatever. The same issue comes in that the source of the particles could be diffuse. And if I want to make it better resolution on my instrument, I collimate down that light source. Well, I'm actually rejecting particles just like I'm rejecting light. There's light that comes and hits the back of that baffle and, is absorbed or reflected. So I'm reducing my signal strength, but I'm improving my resolution. And there's a trade-off you make there of, you can have a very strong signal with lousy resolution, doesn't tell you much. A very precise resolution with a very low signal strength. At some point, you're burying the signal to noise, and you've got to use time averaging effects. So there's a whole area of spectroscopy. And I suppose I spent most of my career, when I think about it, most of my career in research, all of it in research, and when I was in business, and when I was doing my graduate degree, it was all in spectroscopy of various kinds. Electron spectroscopy, ion spectroscopy, and a little bit of photon spectroscopy, but not so much. But what I find is, as a spectroscopist, I can look at this and I know what's going on, because that skill set is transferred from one technology to another. So I could talk to an astronomer about their instrument, and I'd be an informed layperson. I wouldn't know in precise detail, but I'd have a really good idea of the trade-offs they make. And so could ask really good questions and can get up to speed really quickly. And so an astronomer who worked with a spectroscopy system could come to an electron beam system like I have and would also be able to ask really smart questions about it. And there are these little areas in engineering and in science where they transcend technology. And you can have a very nice life, being an expert in this area, and you can actually go from one technology to another with relatively straightforwardly. So for instance, there's the American Vacuum Society. Back in 1980s, you'd go to the American Vacuum Society and there would be thousands of people at this meeting. And they would have 17 parallel sessions of papers being given. So you'd be spoiled for choice. It would go from everything from nuclear engineering all the way across to making potato chip bags. It's like it's a whole range of things because they all use vacuum science. And if you're good at vacuum science, you can kind of hop from one place to another. And the same goes for this spectroscopy. So we often collimate our instruments. Going the right way. We often collimate our instruments. And so the next question is, well, what happens with the collimation? A very interesting thing happens, and that is this. There's three possibilities. The wave is smaller, the wavelength is smaller than the gap. So lambda is less than gap. Or lambda is about the same as the gap, or lambda is less, oops, did that wrong. Lambda is less than, yeah, lambda is greater than, I'll get it right eventually. Lambda is greater than, there's lambda and there's the gap. Lambda is greater than the gap. And you get this sequence of events. When the wavelength is smaller, much smaller than the opening, then all that happens is you reflect off some of that energy, and inside this region here, you'd get no wave energy, and all your wave energy would be defined in a nice beam. That's a nicely collimated beam. If you imagine being on a boat in a harbour, then if you had your boat here, you'd feel no waves. But if you happen to put your boat here, you'd feel all the waves. And if you happen to be down here, you'd feel no waves. Now, if the wavelength is about the same width as the gap, what starts to happen is you go from having this straight through direction becomes irrelevant, and you start getting this I want to say cone, but a cone is three-dimensional. You get this feel like this triangle of energy coming out. And so if you're over here in this boat, now you start feeling a wave, and now you start feeling a wave. You won't if you're really over in the lee of the wall, but you would, even if you're not directly in front of the mouth of the harbour. And if we go to this, where the wavelength is actually bigger than the gap, so now the gap is really small, then what you get is it's basically like a point source of light. It's like having light going in. It's like you put the light bulb there and the light was going out in all directions. That's not clear. That's not going to be indicated by the particle nature of light. But it's very clear from the wave nature of light, as we'll see later on. And so sometimes we don't need to worry about the wave nature of light because, we kind of like dealing with, small wavelengths and big gaps. And other times we need to worry about the wave nature of light because we've got small openings and big waves. So we say if the barrier opening is bigger than the wavelength of the wave emerges from the barrier, continues in a straight line. And if it's about the same sign, the wave spreads out in all directions. And if the diameter is all directions, not really all, is it? It's kind of large direction. I don't like that word all, even though I wrote it. I don't like that. And then if the diameter is much smaller, then it can be, the light can be approximated as a point source. Cool. Okay. And that's Huygens. Well, we can get this kind of thing from Huygens. So what Huygens said? Huygens said, let's imagine that light works like this. It doesn't, but let's imagine it works like this. I can take a wave front, so notice the language. I can take a wave front, and I can have on here a whole series. I can put along here a whole series of points, like dropping pebbles into a pond. And after a certain point, I will take a picture of what I see, looking from above. And what I see is ripple, 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 ripple. And I go, all those ripples are forming another wave front. And so I can imagine dropping a whole bunch of pebbles in the pond and wait and take another picture. Ripple, 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 ripple. And I can say all points on a given wave front are taken as point sources for production of spherical secondary waves. I'm talking about ripples on a pond, so I'm using a two-dimensional analogy. But in three-dimensional space, it would be a three-dimensional secondary wave. And they call these wavelets. Wavelets propagate, that means travel outwards with speeds characteristic of the wave's medium. If they're in some medium, because the speed of light is faster, they go further. In other mediums, because the speed of light is slower, they go less. That's what's determining, when I did this thing with the marching soldiers, it's this analysis that tells you how big a step the soldiers are taking. It's that, how far do you travel before you form the next wavelet? Isn't this basically setting up this bit, where we just have a series of wavelets? This is how Huygens was able to show what happens with refraction. And then it goes, after some time has elapsed, the new position of the wave front, surface tangent to the wavelet. So you draw a new wave front, surface tangent. It's useful to consider the rays. The rays of a given wave are perpendicular to the wave front. So if we do this, we'll get the ray going in that direction. But now let's take a point where we just drop one pebble in. And so now we have a spherical wave front, and we can drop a whole bunch of pebbles on that one, and we get a series of, and can you see how this light is going in all directions? All because of waves, you know? So particles wouldn't give you that. You put a particle in, what does the particle do? Well, it's not a good way of thinking about it, you know? But waves do. And we can see here, let me just follow this. So now when we get here, this wave, oh, it doesn't travel as far. So there's that, and that wavelet travels just as far, and that wavelet travels just as far, and that wavelet travels just as far. So we get that, and then this guy has to match up. And now we put dot, 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 and this one doesn't travel so far, and this one doesn't travel so far. But this one does, and this one does. So we end up with that, and then we go. So you see how this is a nice system to go with. Cool. So I need to sort out the order of some of those notes, because I think I should have had the equations a bit earlier, and I might have moved it back by mistake. So, cool. So let's start.